In example 1, we saw how ramping the current in a solenoid resulted in a changing magnetic flux in the solenoid that produced an electric field intensity. If the ramping current produced an increasing magnetic flux in the z direction, if you look through a cross-section of the solenoid, so here's the cut through representing the solenoid, the resulting electric field intensity are circles around the solenoid. In example 2, we put a conducting material that had a total resistance of 6 ohms that was in the form of a ring around the solenoid. With the solenoid producing an electromotive force of 6 volts, the result was 1 amp of current flowing around the conducting ring. Now we're going to look at what happens if you cut the ring in half and remove half of it. Let's again ramp the current in the solenoid to produce an electromotive force of 6 volts. Faraday's law tells us that the integral of E dot dl around the solenoid will result in 6 volts, and that's true even if we go through the conductor. But if there's an electric field intensity inside the conductor, then a current is going to flow. But a current can't flow because there's not a continuous path for the current. Let the current in the solenoid be 0 till t equals 0, and then at t equals 0, the current is ramped so as to produce an electromotive force of 6 volts. So at t equals 0, just after the current starts ramping, the electric field intensity will be the circles around the solenoid of value 6 over 2 pi rho volts per meter. So initially we have that electric field intensity inside the conductor. So initially there will be a current flowing in the direction of the electric field intensity. So we'll get positive charge building up on the top part of the conductor here and negative charges building up on the bottom part of the conductor. The presence of these positive and negative charges will result in an additional electric field intensity that emanates from the positive charges and terminates on the negative charges. The charges will build up until the electric field from the charges cancels the electric field from the changing magnetic field inside the conductor and resulting in 0 current flow in the conductor. Outside the conductor, the electric field from the charges will add to the electric field from the changing magnetic flux so that the integral of E dot dl through a closed path that goes through the conductor will still sum to your electromotive force of 6 volts coming from your solenoid. Let's attach a voltmeter with the positive terminal to the top part of the half ring and the negative terminal to the bottom part of the half ring, and the ring, leads, and voltmeter are all in the same plane. Let's take the path of integration through our half ring conductor, through the upper lead, through the voltmeter, and through the bottom lead back to the half ring conductor. Putting your right fingers in the direction of integration, your right thumb points into the page. The integral of E dot dl around this path is equal to minus the change in flux with respect to time into the page inside of this area right here. The area defined by our path of integration. So that is equal to the change in flux with respect to time out of this area, and the only place you have a changing flux is the 6 volts coming out of the page from your solenoid. Assuming the leads and the half ring are very good conductors, there's little voltage drop across the leads and the half ring, so the integral of E dot dl will just be determined by the voltage drop across the voltmeter, so the reading on the voltmeter will be 6 volts. Let's attach a second voltmeter to the same points on the ring, but position it to the left of the ring, and again the voltmeter, leads, and half ring will all be in the same plane. Our path of integration will again be clockwise. We'll go through the lower lead, through the voltmeter, through the upper lead, and through the half ring conductor. So putting your fingers of your right hand in the direction of the integration, your thumb points into the page, and you want to know what is the change in magnetic flux with respect to time in this area defined by our path of integration. There is no magnetic flux through this area, so d phi dt inside our path of integration is 0. Again, assuming very good conductors will have no voltage drop across the leads and through the half ring conductor, so the only drop will be across the voltmeter. So the second voltmeter will read 0 volts. So we have 2 voltmeters attached to the same point in our circuit, but voltmeter 1 is reading 6 volts, while voltmeter 2 is reading 0 volts. So Faraday's law tells us the positioning of a voltmeter has an effect on the reading. One final thought. What if we took the path through the 2 upper leads, through the voltmeter on the right, through the 2 lower leads, and finally through the voltmeter on the left? So now the surface enclosed by our path of integration is this region. And the electromotive force through that region is 6 volts. The only change in flux with respect to time through this region is again our solenoid, which is now enclosed by this larger path. So the integral of E dot dl around this path will get minus VOM2 plus VOM1. Substituting the results we found earlier for VOM2 and VOM1, we see that we get 6 volts on both the left and right sides.